Hello, everyone. Welcome to the lesson on principles and applications of mechatronic systems. I'm the lecturer, Liang Guangrui. Today we look at Chapter 4, Servo Control Technology, Fundamentals of Stepper Motor, Part 1. 1. Introduction. Looking back at the lesson motor and drag, we have mastered basic motor control, start-stop, forward and reverse, speed regulation, and variable frequency speed regulation technology, which can achieve conventional speed regulation. However, in the face of high-precision torque, speed control, and precise positioning scenarios, the knowledge above is insufficient. Now, the servo system needs to be used to achieve more accurate control. Servo technology integrates closed-loop feedback, real-time communication, and motion algorithms to achieve micron to nanometer level control of position, speed, and torque. For example, the fly shear system uses a 23-bit encoder to achieve a cutting error of plus or minus 0.05 millimeters. The electronic cam achieves synchronization with a phase difference of plus or minus 0.5 milliseconds and a tolerance of plus or minus 1 millimeter at a linear speed of 2 meters per second. The repeated positioning accuracy of industrial robot is 0.01 millimeters. The positioning accuracy of maglev planar motor of lithography machine is less than 1 nanometer. These cases highlight the important role of servo systems in modern industry. The core indicators of the servo system include a 23-bit encoder with a resolution of 0.0007 degrees, EtherCAT bus synchronization cycle 250 microseconds, and various anti-interference algorithms. In the market, permanent magnet synchronous motors account for 68%. Brushless DC motors account for 29%, and stepper motors are mainly used in low-cost and low-power fields. Traditional servos mostly use motor plus reducer plus screw, but there are problems such as efficiency loss, 70 to 85%, error accumulation, and complicated maintenance. Direct drive motors, DDL or DDR, use electromagnetic direct drive to eliminate transmission losses and improve dynamic response. Maglev trains, DDL, and torque motors, DDR, are typical applications. 2. Development of stepper motor. Next, we delve into today's topic, fundamentals of stepper motor. First of all, let's look at the development of stepper motors. Stepper motor is a motor controlled by electric pulses. Its movement mode is step-by-step. Every time an electric pulse signal is input, the motor rotates at a fixed angle, step angle. The greater the frequency of the electric pulse signal, the faster the rotation speed. So stepper motor is also called pulse motor. Stepper motors have gone through 3 development stages. In the early 20th century, they were used in simple positioning scenarios such as telegraphs and early computers. In the middle of the 20th century, with the development of electronic technology, open-loop control was realized in CNC machine tools, printers, and other fields. After the 1970s, microprocessor and digital control technology promoted its accuracy and expanded to industrial automation, medical equipment, and other fields. Nowadays, stepper motors are widely used for low-cost and high-reliability positioning in CNC machine tools, 3D printers, robots, medical equipment, and other fields by virtue of their advantage of open-loop control. 3. Structure and classification of stepper motor. Next, we focus on the structure and classification of stepper motor. Stepper motors are divided into 3 types according to the principle of torque generation: variable reluctance, permanent magnet, and hybrid type. Variable reluctance non-magnetic rotor has small step angle, 1.2 degrees. Low cost but low efficiency in large heat generation. The permanent magnet type has a permanent magnet rotor, which is large torque and good dynamic performance, but a large step angle, 7.5 degrees or 15 degrees. The hybrid type has the advantages of both, such as large torque, small step angle, 0.9 degrees, strong dynamics, but complex structure and higher cost. Stepper motors are divided into the series of 2-phase, 3-phase and 5-phase, according to stator windings. 2-phase hybrid stepper motors account for over 97% of the market share. Because of their high cost performance, they have better results when combined with micro-stepping drivers. Its basic step angle is 1.8 degrees per step and can reach 0.007 degrees after micro-stepping. 4. Working principle of stepper motor. Let's study its basic working principle in detail. Stepper motor achieves accurate position control and movement, mainly based on two basic principles: reluctance minimization principle and electromagnetic induction principle. Variable reluctance stepper motors operate on the principle of reluctance minimization, and the magnetic flux is closed along the reluctance minimum path. When phase A is power on, it becomes an electromagnet. The magnetic field attracts soft magnetic materials to align with the smallest air gap and the smallest magnetoreluctance. Variable reluctance stepper motor uses the change of magnetic field of stator winding to drive the rotor teeth to align with stator teeth to realize stepping motion. Taking the 3-phase single 3-step as an example, the stator has 6 teeth, 3-phase windings, and the rotor has 4 teeth. When the power-on sequence is A to B to C to A, the rotor rotates counterclockwise. When A to C to B to A, rotate clockwise. The step angle is determined by the tooth pitch of the rotor rotated in a single commutation. For example, if the rotor tooth pitch is 90 degrees, the single step rotation is 30 degrees. 3-phase a single 3-step power-on mode easily leads to rotor oscillation. 3-phase double 3-step conducts 2 phases at the same time, such as AB to BC to CN, and the magnetic field is continuously switched, which can reduce oscillation. 3-phase 6-step adopts single-phase and 2-phase alternately power-on mode, such as A to AB, to B to BC, to C to CN, and the step angle is halved, that is, half-step mode, which makes the movement smoother. Micro-stepping drive technology can improve accuracy and achieve micro-step control by adjusting the proportional micro-stepping step angle of adjacent phase parts, such as micro-stepping to 1/4, 1/8 steps, etc., while suppressing torque ripple and noise, making the operation more smooth and widely used in high-precision positioning scenarios such as 3D printing and precision instruments. Let's look at the principle of electromagnetic induction and the working principle of permanent magnet stepper motor. Permanent magnet stepper motor is based on the principle of electromagnetic induction. The stator winding forms electromagnetic poles after power on, which interact with the magnetic field of the rotor permanent magnet to generate torque. The rotor is a permanent magnet, and the stator is a multi-phase winding. The magnetic field attracts each other at different poles and repels each other at the same pole, driving the rotor to align the magnetic poles. In terms of power-on sequence and direction control, if you want the rotor to rotate clockwise, you need to switch in the order of A plus, to B plus, to C plus, to A minus, to B minus, to C minus. Rotating counterclockwise requires switching the power-on sequence in reverse direction, such as A plus to C minus, to B minus to A minus. The step angle is determined by the number of rotor poles and the number of stator phases. The typical step angle is 7.5 degrees or 15 degrees. Similarly, permanent magnet stepper motors can also adopt micro-stepping in half-step modes to achieve half-step or micro-step control by alternating single-phase and two-phase power on or adjusting the curve ratio, which can improve the smoothness of motion and reduce vibration. Hybrid stepper motor combines the advantages of permanent magnet and variable reluctance motors and drives the rotor through the synergistic effect of magnetic field and reluctance. The rotor incorporates axial permanent magnets and soft magnetic teeth and slots, which are misaligned with the stator teeth by half a tooth pitch. The stator is a multi-phase winding, which forms electromagnetic poles after power on. When phase A is power on, the stator magnetic field attracts rotor teeth to align. After the polarity of phase B is switched, the rotor is pushed to turn to a new balanced position, and the multi-teeth are stressed synchronously to enhance the torque stability. The power-on sequence of the hybrid stepper motor determines the direction of rotation. When the power-on sequence is A+, to B+, to A-, to B-, the rotor rotates counterclockwise. When A+, to B-, to A-, to B-, rotate clockwise. The step angle is determined by the number of rotor teeth and the number of stator phases, with a typical range of 0.9 degrees to 1.8 degrees. Hybrid stepper motors are widely used due to their precise tooth slot design, which enables high-precision control. The rotor includes axial permanent magnets and soft magnetic teeth and slots, which have the same tooth pitch as the stator, but are circumferentially offset by 1/4 of the step angle. After the two-phase winding of the stator is power on, an electromagnetic field is generated, and the teeth slot is misaligned to form a minimum reluctance path. When the magnetic field is switched, the rotor is driven by continuous torque to achieve micro-step motion, which has the advantages of high torque and high resolution. In addition, the step angle of the hybrid stepper motor is determined by the formula theta equals 360 degrees divided by NR times NS, where NR is the number of rotor teeth and NS is the number of stator phases. Taking a typical two-phase motor as an example, the rotor has 50 teeth at each end and a total of 100 teeth, and the step angle is theta equals 360 degrees divided by 100 times 2 equals 1.8 degrees. Its open-loop control characteristics bring it high accuracy in single steps. It relies on manufacturing processes, has no cumulative errors, and is suitable for cost-sensitive scenarios such as printers and automation equipment. 5. Summary. Through today's lesson, we have mastered the fundamentals of servo control technology, especially stepper motor. We have learned about the wide application of servo systems in many fields such as metal processing, packaging industry, CNC machine tools, industrial robots, etc. Meanwhile, we've also understood the unique advantages of stepper motors in small and ultra-small civil applications. Through detailed study of the structure, classification, and working principle of stepper motors, we've understood how stepper motors convert electrical pulse signals into angular displacements or linear displacements. This lesson ends here. Thank you for listening. See you next time.